All right, greetings everyone. Welcome to the second part of the video for section 4.6, continuing on with some more applications of exponential functions. I should also mention about this meme here. I feel like students have told me who this person is. In this picture, I'm going to be honest, I have no idea. A Jonas brother, maybe? Yeah, not sure. All right, so let's talk now about doubling time. So we talked in the previous video about half-lives. Let's now discuss doubling time. So as you might imagine, as the name implies, the doubling time for something that is increasing is the amount of time it takes for the quantity to double. So to be double the amount that you started with. And the interesting thing about doubling time, just like with half-lives, is that it doesn't matter what amount you start with, the amount of time that it takes for that to double will be the same regardless of that amount. So the amount of time that it takes for a substance to go from 1 gram to 2 grams would be the same as the amount of times it takes to go from 8 grams to 16 grams. All right, so let's look at an example using this. So we're told that a bacteria initially contains 2,500 bacteria and doubles every half hour. We need to find the size of the bacterial population after 80 minutes and also after 6 hours. Now, just like with previous problems, before we can start to attack these two parts here, we need an equation of some sort. And since we know we're dealing with exponentials, we'll probably use f of x equals a times b to the x, which we know that we're going to need some points to work with that, and or the initial value, which we do have the initial value, right? We're told that initially there are 2,500 bacteria, so that can go in for the value of a. So if f of x equals 2,500 times b to the x. And then we need another point with some information. So we're told here that the amount doubles every half hour. Now, just like with most of these types of problems, probably we'll have our time as our inputs, so that half hour, which we could write as 0.5 if we're doing as hours, but I also noticed that one of the problems here uses minutes. So to keep things simpler, I'm just going to write this in terms of minutes. So after 30 minutes, well, if it's doubling every half hour, we start with 2,500 bacteria. What's going to be the amount we have after a half hour? Right, that would be 5,000 bacteria. Okay, so now we have another point we can use to solve for the value of b. So we'll go ahead and plug this in. So we have 5,000 equals 2,500 times b to the 30th. We'll divide by 2,500 on both sides. Okay, so we'll end up with b to the 30th equals 5,000 divided by 2,500 is 2. And to solve for b, we need to take the 30th root on both sides. And so on the left there, we'll just have b, and then we'll take the 30th root of 2, which we can go ahead and plug into our calculators. That's what I'm doing right now. And I get 1.0234. And in fact, I'm going to use a few more decimals here. I'm going to do 3739. Now, part of the reason I'm doing this is that with problems like these, where we're starting to use values that we've calculated to then calculate new values, we want to maintain as much accuracy as possible. And the reason for that is as we start to round off, even if we were to round this to, say, 3 decimal places, we're going to lose a lot of accuracy in this. Okay, so we want to maintain and be as accurate as possible. And in fact, if I really wanted to be totally accurate, we could just use the 30th root of 2 instead for b and plug that into our equation. So whichever we prefer. All right, so I'm going to plug in this value here for b into the equation. We also know the value for a. So we know that our function looks something like f of x equals 2,500 times 1.02333739 to the x. And now we can solve the two parts of this problem. So the first one asks us to figure the amount of bacteria after 80 minutes. So then we can just plug in 80 for x, so do f of 80. I'll write that all the way out right now. I'm going to plug this into my calculator. Again, I'm going to use all of those decimals I've written out there. And when I do that, I get that the amount of bacteria is 15,874.020, and this would be bacteria. And then for the second one, we need to find the amount after 6 hours, but we're not going to just do f of 6. And why is that? Recall that for our units on x, right, we did those in terms of minutes. So we need to think about how many minutes there are in 6 hours. If you multiply that out, you get 360 minutes, because there's 60 minutes in an hour. We can go ahead and plug that in. And if we do that, we end up with, according to my calculator, 10,240,028.83 bacteria. Okay, so those would be our two answers here. Now, I want to look at really quickly what would happen if, for the second one, I had only used 1.023 to the 360th. And I'm doing that in my calculator right now. And when I plug that in, I get the number of bacteria as being 8,977,763. Which you can note is quite a bit off from 10 million. So that's why with numbers like these, or with problems like these, we want to try to maintain as much accuracy as possible so we don't have errors in our work like that. Okay, let's look at another problem. So going back to example we did earlier in this chapter. So remember that check that Grandma gave you with the extra zeros? Suppose you invest Grandma's $1,000 in an account that pays 6% interest compounded weekly. We want to figure out how much time it will take for the investment to grow to $4,200, which will be approximately enough for a full year of tuition at Pierce. Now notice in this problem, we're told that we have 6% interest compounded weekly. And that should clue us off to the formula we need to use, which would be our compound interest formula. So if you remember, that's A of t equals A times 1 plus R over K to the K times tth power. And then we can go ahead and plug in the information we have for that. So first of all, we know we're starting with $1,000. So that will go in for a value of lowercase a, since that's our starting value. We're told we have 6% interest compounded weekly. So that 6% will go in for a value for R. And let's note that we got to put that in as a decimal, as 0.06 divided by compounded weekly. So remember, if something is compounded weekly, that means it's compounded 52 times per year, not 7. Remember, the value for K is the number of times compounded per year. So there are 52 weeks in a year, so 52 goes down there for K. It also goes above for the K up there. And then we're trying to figure out how much time it'll take for our investment to grow to $4,200. So we're looking for an output of 4,200, and we're solving for the value of t here. Okay. All right, so let's go ahead and do this. We can start by dividing by 1,000 on both sides. Okay, when we do that, these cancel out. 4,200 divided by 1,000, I believe that's going to give us 4.2 equals 1 plus 0.06 to the 52nd. And again, I am purposely not simplifying that 1 plus 0.06 to the 52nd, or divided by 52, because we want to maintain accuracy here. We know we're trying to solve for something in the exponent up here, so we know we'd take a log now of both sides, which will allow us to move the exponent down to the front. When we do that, we'll now have log of 4.2 equals 52 times t times log of 1 plus 0.06 divided by 52. And then we need to isolate the t. And notice the t is being multiplied by both of these things here on the right-hand side. So what we can actually do is divide by both of those things. So we could divide by 52 times log of 0.06, 1 plus 0.06. Oh boy. Let me try that again. Log of 1 plus 0.06 divided by 52. Okay, when we do that, these cancel. And we just have the t on the right-hand side. And left-hand side, we have log of 4.2 divided by 52 times log of 1 plus 0.06 divided by 52. We'll very carefully put this in the calculator. When I say very carefully, that we want to have this whole top thing divided by this whole bottom thing. So I need to make sure that I use parentheses here. So I'll do log 4.2 divided by parenthesis 52 times log of 1 plus 0.06 divided by 52. Close all my parentheses. And when I do that, I end up with 23.932. And remember, the value for t is always measured in years. Okay, so it's going to take a while for grandma's money to equal enough for us to pay for a full year at Pierce. So yeah, we might need to find other funding sources. All right, that's it for now. Thank you for watching.